Okay, so one of the first things that we need to understand, or that we need to learn, is the use of vectors. Many of physical quantities are described by what's called vectors. Some of you may be familiar with the vectors. Most of us, where we are more familiar, are what we call scalars. So scalars, can everybody read my handwriting? It's not better on the blackboard, I can tell you that. So scalars are numbers, are quantities, are things that can only be described, or that can be described with only one magnitude. So we only need one number to describe them. You can think of them as a magnitude or the size. Okay. Things, for example, like temperature. To describe the temperature of the room, the only thing that you need is one number. You know that the temperature of the room is going to be 75 degrees. So you know that that's the temperature in the room, and that's all that you need. Things like time. You can tell 5 seconds, 10 seconds. It's going to be 3 a.m., 4 a.m., or 5 p.m. You only need one number to know what time it is. Things like weight. Also, like if you want to know the weight of a person, you only need one number to describe the weight. Okay. Now we have also what's called vectors. Okay. Vectors are a little bit more complicated. Vectors are things that require a magnitude and a direction to be described. So here we need the magnitude and a direction. Okay, and I'm for the class, I'm going to assume that most of you don't have any background in physics. I know that some of you have taken physics in high school, but that may be a long time ago. So I'm assuming that it starts from zero. So it sounds a little bit repetitive for some of you. Just bear with me. It will get up speed really soon. So for vectors, we need a magnitude and a direction. So things, for example, like a force. When you apply a force, you don't only need to know how big that force, how hard you're going to push. You need to know in which direction you're pushing. Because if you know the direction, it can change completely what's going to happen to the object. So if you have a little kid and then you push down, well, you're going to make that kid sit down. If you apply a force up, you're going to throw the baby up, and you're going to throw it and it's going to have fun. Okay. So depending on where you apply the force and how you apply the force is going to be different. There are other examples. If I have a book and I apply forces on equally in opposite sides, I can push really, really hard. And as long as the two forces are the same, this book is not going to move. It may deform, but it's not going to move. But if I push at different parts of the book, like my hand is on the top and my hand's on the bottom, and I apply a force, it's going to rotate. Okay, so how you apply the forces, where you apply the forces, is going to create different effects. So one of the things that we're going to try to do is to analyze forces. So forces is one of the quantities that we need to describe by using vectors. Now, one of the consequences is that everything else that depends on force is also going to be a vector. So we're going to see, okay, a force is a kind of vector, but also we use forces to describe pressure. So pressure is going to be a vector. We use forces to describe something that's called impulse. So impulse is going to be a vectors. And all these little things, everything that derives from the forces is going to be also a vector. Another one that is kind of weird is displacement. Okay, and displacement is something also that we describe as a vector. Now, displacement is a little bit different than distance, at least in physics. So okay, so displacement is a little bit than distance. Distance is the total length that you move from one point to another. So, for example, let's say that I start walking and I start at point A, and then I'm going to end up at point B. Okay, so I can do it different ways. I can go from those points and different paths. So I can go and do something like this. I can do something like this. I'm going to call this 1. I'm going to call this 2. And I can do something like this. Okay, so one of the difference is that to calculate the displacement, the only thing that I care is the initial position and my final position. That's the only thing that I care. I don't care the path. I don't care how long it takes. I don't care if I stop in the middle. I don't care if I do the longest possible path. It doesn't matter. The only thing that I care for displacement that I care is the final and initial position. Okay? For distance, it matters where you go and what path you do. And then for distance, we can say, okay, this distance, we know that distance 2 is going to be the shortest distance. And then distance 1, path 1 is going to be the medium distance, and path 3 is going to be the longest distance. Okay, so distance is the length of the path. Okay, but displacement is not. Displacement, the only thing that cares is what is initial and where is the final position. For most of the physics quantities that we're going to use, for most of the calculations that we're going to be using, we use displacements. We don't talk about the distance, or very few occasions. Okay, but we care is that displacement. And as a consequence, well, the displacement of these 3 paths, the displacement of path number 1, 2, and 3 are the same, even though they describe completely different things. Okay, that's kind of weird, and it affects a lot of calculations. So we use displacement to calculate velocities, accelerations. It also applies to forces, applies to work, applies to energy. We use displacement and we use displacement to derive many other quantities. So it affects everything. You're gonna see me very often to describe something as delta x. So if you imagine that this is in the x direction, delta x is a vector and it's gonna describe the displacement. Okay. Now this delta x, it can be delta x, delta y, delta f, delta whatever, delta t for time. Delta is a mathematical operation, and delta basically means final state minus initial state. So if we're talking about position, it will be the initial position, sorry, the final position minus the initial position. If we're talking about time, it will be the final time minus the initial time, and so on. So for delta x, that means the final value of x minus the initial position of x. for delta t, that there will be time. It will be final time minus initial time. Okay, so if I want to calculate the displacement of these drawings over here, that will be just the B position, that's my last position, minus A. Okay, makes sense? Alisa?
Yes.
Make sense?
Yes.
Okay. Noah? Aubrey? Noah too. And Alexis? Paige? Trinity? Christopher? Alex. Okay, well, it's not even close. Is there a Christopher in this class? Okay, no. Jacob? Okay. It's gonna take me a while to learn the names. Just give me. Alexis. Make sense? Trinity? Alex? Alex or Alex? Alex? Alex. Okay, make sense? Okay. Okay, so in order to work with vectors, one thing that we need to do is to find a way to quantify the vectors. And to do that, we usually place the vectors in a coordinate system, in a reference point. We need to give them a way to compare different vectors with the same scale. So what we use is what is called the Cartesian plane. And the Cartesian plane is just two straight lines perpendicular to each other. So it's just going to look something like this. Okay, the horizontal axis, we call that the x-axis, and the vertical axis, we call it the y-axis. Okay, right now I'm going to be talking about meters. So all my distances are going to be in meters. So this is going to be meters. This is going to be meters. The Cartesian plane is divided in 4 quadrants. So this is the quadrant 1, 2, 3, and 4. So sometimes when you are doing operation with vectors, you know that the result is going to be in the 3rd quadrant, or it's going to be in the 4th quadrant. Or if you want to identify vectors in the plane, you can figure out exactly where it's going to be. And that helps you a little bit with the math sometimes. Okay, so let's say that I have the Cartesian plane with x and y, and I'm going to have a vector and the vectors are usually represent like that, just like an arrow. The tip of the arrow just represents where is the final point, and here, so this will be our final point, and this will be my initial point. Okay, so let's say that that's the vector, and that's the vector that I'm going to be describing. And this vector can represent a velocity, it can represent acceleration, it can be representing a displacement, it can represent anything that we want. Right now, I don't care exactly what it is. We're going to be working a little bit with the math. So I'm going to say my initial point of the vector is at a coordinate 1 position in x, and 1 in y. So the initial position is going to be 1, 1. So that 1, 1 represents the point in space. The final position, well, that will be in 6, 4. Okay, so to calculate the displacement of this thing, or the size of the vector, what I'm going to do is going to do final position minus initial position. Initial position. So that will be, my final position is 6, 4 minus 1, 1. And what I'm going to do is subtract the x to the x. Oops. Sorry. So what I'm going to do is I'm going to subtract the x with the x's and the y with the axis. So yes.
And that's to find the displacement, correct?
Yes, this is just to calculate the displacement or the magnitude of this vector. Oh, sorry, this vector. Not the magnitude, just the vector. So this will be 5, 3. If I can still do math, that will be 5, 3. So the vector, this vector is 5, 3. Sometimes, well, to distinguish between vectors, you notice that and points. So these are points, so we use parentheses. And with vectors, sometimes we use square brackets. Okay, don't worry so much about that. Okay, so that 5, 3, that represents the vector. Okay, those are the components of the vector. It's a vector that has one size is in the x direction has a size of 5, and in the y direction has a size of 3. So so to calculate the magnitude of the vector, and the magnitude of the vector is represented with these kind of straight lines around the variable of the vector. We use this a square, sorry, the x component of the vector square plus the y component of the vector square, and then the quantity, we get the square root. Okay, I'm gonna do it in a different page, and it seems that I'm getting this formula from nowhere, but I think you're familiar with this formula. So I'm gonna redraw this vector. And I'm gonna change the vector. So instead of having it in free space, I'm gonna put the origin of that vector, I'm gonna put it here in the intersection of the two axes. And I know that, well, I would say this is gonna be 5. Sorry, this is gonna be 5, and this is gonna be 3. Okay, so it's exactly the same vector, same x component, same y component. The only thing that I did is that I moved the vector from whatever it was, I move it to the origin. Okay. And here you can see that I have a triangle rectangle. Okay. So I have a triangle rectangle. One size is 5, the other one is 3. So if I ask you to calculate what is the length of the hypotenuse, well, the length of the hypotenuse, you know there's going to be, if this is C, you know that C is going to be 5 squared plus 3 squared, square root of that. So in vectors, we'll call this 5. We call the x component of the vector. The 3 will be the y component of the vector. And the hypotenuse, we call it the magnitude of the vector. Yeah? Make sense? Kind of? Okay, so for this case, the magnitude of the vector will be 25 plus 9, square root of that, that's 34, square root of 32. I mean, the square root of 34. No idea how much is that.
I mean, it's going to be close to 6, like 5.8, but.
Kind of, yeah. 34. Yeah, 5.5. Okay, so that's the magnitude of the vector. Okay, make sense? Now, we know that to have a vector, we need two things. We need the magnitude, we know the direction. The direction is measured in degrees, and the direction will be this angle over here. And here's when you need to remember your trigonometry. Do you guys remember how to calculate the angles in triangle rectangles? Page? How do you calculate it?
Like sine, cos.
Yeah, sine, cosine, tangent, all that. Everybody remember that? Yeah. So there are different ways that you can do it for this angle. So I know that tangent of theta is going to be opposite over adjacent. In this case, the opposite is going to be my y component of the vector, and the adjacent is going to be the x component. So this is going to be just delta y over delta x. Sorry, the y component over the x component. So if I want to calculate the angle, well, that will be the arctangent of y over x. You can, I mean, if you have the three lengths, if you have the adjacent, opposite, and the hypotenuse, you can use any trigonometric function. So you can do sine of theta. You know, the sine of theta is going to be, what is it? Opposite over hypotenuse. And cosine of theta will be adjacent over the hypotenuse. So you can use either of those equations, and you should get more or less the same number. So I'm going to do the arctangent. So that would be 3 over 5. So that's 59 degrees. Yes.
Can you real quick just remind us how to put the arctangent in the calculator?
Sure. It depends on your calculator. But normally, all calculators are going to have something like that. So you're going to have your trigonometric functions. So I have sine, cosine, tangent. And then you're going to have an inverse function, an inverse button somewhere in your calculator. So in my case, it's this white thing. So I just press, I have the number. My calculator is a little bit different, but then you just have the number that you want, and then inverse function of tangent, and that should be enough.
Okay, thank you.
I don't know if you have your calculator with you. So we're gonna do a couple of exercises. So if you have your calculator, just bring it out, and then we can try to do some problems. Okay. One thing, this before we do the exercise. So this trick that I use of having one vector and then just move it to the origin is perfectly fine one of the things with vectors is that the only thing that you need is the magnitude of the direction. And as long as those things remain unchanged, you can move a vector wherever you want. So you move it to the origin because then you simplify a little bit the math. So you can have a vector that looks like this, and then you can displace this vector here, and as long as the magnitude and directions are the same, it's perfectly valid. It's something that's very weird with vectors, but that's why we're gonna use this a lot. So it doesn't matter what vector you have, you can displace it, and as long as you don't change the magnitude or the direction, it's gonna be exactly the same. Okay? So really quick, what I want you to do is to calculate the magnitude and directions of the following vectors. So I'm gonna have this over here, and I'm gonna have this vector. Okay, let's start with B. I think that's a little bit easier. And then we do A. If you're done with B, you can do A. You go. Yeah.
close to what they want.
Oh.
And it was hard to do the problems. What would it calculate? Just
Yeah,
just
I-
you have a phone? You have a calculator. Fancy. That's pretty cool.
Same paper, I rewrite my notes.
That's pretty cool. Okay, how many of you are done with the first one? Okay, I'm gonna give you a couple more minutes. Okay, I'm gonna do B really quick. So we start at the origin. So if I want to calculate this vector, well, I do final position minus initial position. The initial position is gonna be 0, 0. So that simplifies a little bit of the math. So this vector, and I'm gonna call this vector A just because I cannot think of any other thing. So this vector is gonna be 3, 7. That's gonna be the vector, which is just the same as the final position of that group. So the magnitude of A is gonna be, again, if you imagine this a triangle rectangle, the magnitude is basically calculating the hypotenuse of that vector, of that triangle. So it will be 3 squared plus 7 squared. That's what is 49 plus 9. And Alex,
6/3 of 56 is,
7.6.
okay, I got 7.48.
You got what?
As the square root of 56, I got 7.48.
No, it's 58.
Yeah, it's 58. 7.6. And the direction, again, you can use any of the trigonometric functions. I'm gonna use tangent. So that will be the arctangent of 7/3, opposite over adjacent. So that will be 68.8 degrees. Okay. Have you been able to finish the first one, A? No?
Yeah.
You got you got this one? Yep. Jacob, you got the first one? And way on the back. What's your name again?
Dylan?
Dylan, you got it?
I have not.
Next to Dylan.
Samantha, I have it besides the direction.
You got it?
Besides the direction.
Okay. Okay, we'll go with the direction. So I'm gonna do it also a little bit quick. I'm gonna spend a little more time with the direction. So to calculate the components of these vectors, and I'm gonna call this vector B. So the components of B is final minus initial. So in the X will be 5. And in the Y will be final minus initial. That will be minus 3. Yeah. So those are the components of vector B. It has a component 5 positive in the X direction and minus 3 negative in the Y direction. Okay. So to calculate the magnitude of B is exactly the same thing. It's calculating the length of an hypothesis, hypotenuse. So this will be 25 plus 9. That will be square root of 36, no, 34. So that will be again 5.8. Yeah. Now for the magnitude, sorry, for the direction, we're looking for this angle over here. So it's still a triangle rectangle. It's not that now it's a little bit under, it's below the x-axis. So theta, the arctangent is going to be opposite over adjacent. The opposite is going to be minus 3. And the adjacent is going to be 5. So if you do it on your calculator, you get minus 30.9. Yeah. And that negative 30.9 just basically says that it's below the x-axis. Okay. Now, I'm going to have another vector. This one is going to be in the second quadrant. And it's going to be a vector C. And the components of C are going to be minus 5, 3. So this point over here is minus 5, 3. Sorry. Okay, so notice that it's exactly the same that we have for vector A, just kind of like a mirror image. So now instead of being in the fourth quadrant, it's going to be in the second quadrant. If I'm going to calculate the magnitude of C, I get a 5.8, same as before. And now I want you to try to calculate the direction. So if I do the direction, it's going to be opposite over adjacent. So it's going to be 3 over minus 5. And do that in your calculators. Trinity, what you got?
I don't know if this calculated, but I got a negative 0.5.
Negative 0.5?
Might be in radicals instead of degrees.
Did you got the right results in the previous
Oh,
problems?
I didn't put it in degrees.
Okay, you have in radians? Okay. Yeah, check that your calculus in degrees. Aubrey, what you got?
Minus 30.9.
Minus 30.9. So it's exactly the same result that you got before. There are two different vectors. They are in complete opposite directions. One is in the fourth quadrant and one is in the first quadrant. But if you calculate the magnitude, you get the same magnitude. And if you calculate the direction, you get the same direction. So if you just look at the numbers, if you just follow the math, it's going to give you the impression that the two vectors are the same vectors, because we have said for vectors, the only thing that you need is direction and magnitude. And these two seems to have the same direction and the same magnitude, but they are not. It's obvious that they are completely different. So one of the problems is that your calculator doesn't know where is the vector. It doesn't know if you're calculating a vector because one has a negative y and a positive x, or if you have a positive y or a negative x. In terms of the numbers, in terms of the math, it's going to give you the same results. So when we are working with the vectors, doing the diagram helps. It really, really helps. It's going to tell you where your vector is and what this 30.9 degrees actually means. And that doesn't just means that it's this angle over here. It's measured along the negative x direction. Okay? It gets a little bit confusing. If you follow the calculator blindly, it's going to give you the wrong results, like not the physical meaning of the results. You need to be able to figure out what the calculator is trying to tell you. Okay, so don't follow the math blindly. Do the drawing, do the diagrams, and then you're trying to figure out, okay, what is the angle that I'm trying to represent? Make sense? Ish? Alexis?
I'm just a little confused by what you mean by the calculator is off.
Yeah, so we have these two vectors that they're opposite to each other, but they have the same magnitude of components. So it's gonna give you the same magnitude of the vector and apparently they're gonna have the same direction. But you need to be careful because they basically represent different vectors.
Okay.
So in this case, in the last case, my opposite is this one. Sorry, my adjacent is this side, and my opposite is this one. So this is the angle that I'm calculating. Regardless of what the calculator is giving you, this is the angle that you're calculating. So you just have to be careful of what is the meaning of the value that the calculator is giving you. Okay. Alicia?
Yeah.
Make sense?
Yes.
Okay. Noah? Okay. We're going to stop here. So you have a little bit of time to go to your next class and not be crowded in the hallway. Have a good day and see you on Friday, hopefully with less tech issues. Noah, thank you so much. That was great.